Hello, how are you guys doing today? I can't decide if I'm cold or warm or what, but I'm sitting out on my porch nonetheless. And Josie, say hello. Okay, so today I wanted to talk about the t-test, and we finished up talking about measures of spread the other day on the last video. Okay, so first I want to talk about the t-test. So you can see over here in this diagram here, we have our sample. These are the people that we have pulled in, and they are going to be a part of our experiment. So we've divided them into two groups. And we have our treatment 1, and then we have our treatment 2. So we can go back to our caffeine example, and let's say these are the people we came in with, they're coming in, and we are going to give these people caffeine, and we are going to give these people water, and we are going to see what the reaction times are. And then we are going to get a mean reaction time from our caffeine group, and we're going to get a mean reaction time from our water group. So the only time we can use a t-test is when we have a single factor two-level design. So this is the only time we can use a t-test. So when we have an independent samples t-test, this is whenever we have our two different groups are between subjects. So that's what's represented here in this graph. This would be, we have our group come in, and half of them are going to get caffeine and half are going to get water, and then we're going to test them on the reaction time task. And then we have a dependent samples t-test, and this is whenever we have some sort of relationship between the groups. So in a independent samples, this would also include our ex post facto designs as well, because those are inherently between subjects. But for a dependent samples, that suggests that there's a connection somewhere between the groups. So this is whenever we have our within subjects design. So we have people that are going to come in, and some of them are going to get caffeine and some are going to get water, and then they're going to come in again. And they're going to get, the people that got caffeine are now going to get water, and the people that got water are now going to get caffeine. Interestingly enough, whenever we have a matched groups design, so again, we have come up with some reason for us to match the groups. Going back to our basketball example, maybe we matched people on height or previous experience playing basketball. So they are also connected in some way. So technically, whenever we have a matched groups design, we are going to run a dependent samples because they are still connected in some way because of that we have decided that they are connected on. Okay, so whenever we're doing our statistical analysis on our single factor two-level design, we have certain things that we need in order to understand our data. So first we need our measures of central tendency, and then we need our measures of spread. So again, this is descriptive information. So our measures of central tendency, the one that we are going to be most interested in is of course the mean. And this is going to tell us, describe our data and tell us on average what our people did in each of our groups, in each of our two groups. And then we have our measures of spread. So we're going to see just how much our data in our sample is spread about the mean. So this is going to represent the variability in our data. Okay, so I bring us back to this equation. All of our inferential statistics, everything that we do, whether we're running ANOVAs, whether we're running t-tests, whether we're doing anything, is going to be interested in this particular equation. So we have variability in our data. Our systematic variability, we've gone over this before in the past, our systematic variability is the variability that happens between our groups because of our manipulation. We are hopeful in this caffeine water example that our caffeine group is going to be faster on the reaction time task because we gave them caffeine. So that's our manipulation that we're giving them. So this is systematic. This is what we're hoping to see. This is what we want to see. And then, of course, there's always going to be error because nothing is perfect. We are always going to have error in our data. So then we have, so this is the data between our conditions. We have our two levels, and we want to see differences between them because of our manipulations. This is systematic variability. So then we have our variability within each condition. So these are things like if we think about our caffeine example back whenever we did this a long time ago, or at least it feels like a long time ago now, where we had Barry, and we had Bertha, and we had Beatrice, and they had arm casts and an amphetamine addiction and all of these things that we are not accounting for. there's going to be individual variability that is occurring. There's going to be measurement error. There's going to be these things that we cannot control. This is going to happen within each group. So our people that are getting caffeine, we're not going to necessarily know that Beatrice has an amphetamine addiction, right? We're not going to necessarily know that they've done a reaction time task before. So these are things that are going to be happening, that are going to be error, and we cannot do anything about it. It's just always there. So in order for us to reject the null hypothesis, and again, this is true in every statistical test that we use, it's some variation of this equation where what we want is we want our systematic variability. This is our manipulation. We want this to be the variability because of our manipulation to be bigger than the variability caused by random error. And so we need this numerator in this equation to be larger than the denominator for us to find statistical significance in our data. Okay, so just to give you some information about this jargon, whenever we are talking about systematic variance, we are talking about the variance within each individual group. Systematic error is included in this. So when we see this equation up here and we see, I don't know if I can move myself. So we have systematic plus error up here. Systematic is also representing systematic error. Systematic error is what is happening because of compounds. These are things that we know are affecting the data. This is systematic error, which is also included in the numerator. We know it's happening. Random error is the extraneous variability that we cannot necessarily control for. We try to minimize it as best as possible, but there's always going to be extraneous error in our data. There's always error. So as a general rule, we want to eliminate our compounds. We want to eliminate the systematic error. We want to take this away. We don't want the differences between our groups to be because of a confound. We want it to be because of our manipulation, because we want it to be on purpose. So we want to maximize that systematic variance as best as we can. This comes from our operational definitions, and this comes from pilot studies and all of these things to try and maximize our systematic variance. And we want to try to minimize our random error as much as possible. We can never eliminate it, but we want to try to minimize it. Okay, so let's go a little bit further into variance here. So again, we're talking about standard deviation. We're talking about standard error of the mean. So you'll see these terms when you get into statistics, especially if you find yourself one day in graduate school taking graduate statistics, you'll see these terms thrown out. So I just want to let you know what they mean. So whenever we have a small standard deviation, that means that on average, our data is clustering about the mean. So we have a very small standard deviation. Most of our data points are close to the mean. So we don't have very much variance in our data here. So this is called the homogeneity of variance, or also homoscedasticity. That's the term for that. That means that we have a small standard deviation. That means we have low variance in our data. When we have a large standard deviation, that means that we have a lot of variance. That's going to flatten our curve, and that means that on average, our data points are not necessarily close to the mean. That means our mean might not be that representative of our data. So this means that our data is heterogeneous. It is not clustered about the mean. So this is called heteroscedasticity, and that means that we have a lot of variation in our data. We have lots of spread. We have lots of variance. When we have a small sample size, we are likely to have high variability in that sample, because you and I, if we were to both take a reaction time test, our reaction time is going to be very different, right? So we are going to have lots of variability between the two of us. And then as we increase, our sample size, people are more likely to cluster about the mean. And that's more representative of the general population. Most people, again, when we think about the bell curve, most people are going to be close to that mean. So the higher sample size we have, the lower our variability. And we want to try to lower our variability as best as possible. So small sample sizes causes a much higher variability. Okay. So there's another factor that we need to think about whenever we get into statistics, and that is degrees of freedom. Degrees of freedom, very simply, the very basic definition of this is how free any one individual is to vary. So our total degrees of freedom is whenever we take our overall sample size, which is representative of n. Whenever you see n, that means our sample size. And it can vary -1. So I'm going to use a hat example. I love funny hats. Hopefully you guys do too. So if we think about, let's say we have lots of funny hats and we want to wear a different hat every day of the week. So we have 7 hats down here, right? So we have Monday through Sunday, and we're going to wear a different hat on each day. Well, on the first day, on Monday, we can choose from any of these hats. We have lots of choice. We have lots of variability here. We can pick any of these hats right here. So we can pick any of these. But then on Tuesday, let's say we already wore the lobster hat. So now we only have 6 to choose from. Then the next day we only have 5 to choose from, and so on and so forth. Until the very last day of the week, we would have already have worn, oh, that looks good. Josie just came back out. We would have already worn 6 of these hats. So on the very last day, we don't have a choice anymore. Our options have limited. So we do not have a choice any longer. We do not have the freedom of choice. Instead, we have to wear the last remaining hat. We have to wear, let's say, the Santa hat, because we would wear that last, right? Surely. So that's why, so our very last choice here is not going to vary. It is what it is, and we cannot vary it any longer. So that is why our degrees of freedom is always -1, because there's always one data point that is not free to vary. Okay. So remember when we were talking about distributions and how different our different tests have different distributions. So this is showing a t distribution. So this is the t-test, and again, we're only using this when we have a single factor 2-level design. So whenever we're doing this, our sample size is generally small, and again, we never know what the population mean is. So that's what this is representing here, this sigma. We do not know what the population mean is. There is something out there. We know it's out there, but we just do not know what it is. So our standard normal distribution is represented here in the black. And again, that's showing us our population. That's if we were to have every single person out in the entire world and we were able to test them. So we have unlimited degrees of freedom. Everybody's free to vary. We are testing everybody in the world. So this is our standard normal distribution. But whenever we have a smaller sample size, it's going to be less representative of the population mean, because we have a fewer representative sample. So if we have 1 million people, then that's going to be more representative of the population than if we have 10 people. So that is when we're going to have a lot more variability. So our curve is going to be flatter. It's going to be more spread out. We're going to have higher variability, and it's going to be less representative of the standard normal distribution. So we have the more people we have in our study, the more people we can recruit, the higher sample size we have, the higher the degrees of freedom, the more likely our distribution is going to be representative of a standard normal distribution. So a t-distribution is very similar to a standard normal distribution. We're making the same assumptions that the data is going to have a mean, and most of the people are going to vary about the mean, but as our sample size increases, we are going to be more representative of that general population. So I'm going to stop there for now, and I am going to move forward with the next video momentarily. Thank you.